about is, what is implicit differentiation? What does that mean? Well, you use implicit differentiation when you have a function that's written implicitly. So this is what it means to have a function that's written implicitly versus explicitly. Until now in our class, okay, and most of the functions that you've probably seen in other classes have been written explicitly. A function is written explicitly if you can isolate y. So if I have y equals x squared plus 2x, for instance, notice that I can isolate y. That's what we mean when we say that the function is written explicitly, y as a function of x. When y is not isolated, the function is written implicitly. So, and of course, sometimes you could isolate the y, but sometimes that's a lot of trouble. Sometimes it's not algebraically possible to isolate the y. But just to give you an example, I might have one that looks like this. Now, this one I could isolate y by factoring the y out on the left and then dividing both sides, but I can kind of mess that up pretty easily. Okay, so it's not easy to isolate the y. So then what do we do if we still want to find the derivative of that function, knowing that y really is some function of x, okay, but we don't know exactly what that is if we were to isolate y? We can still find the derivative. That's what we are going to do in this section. So this one is written implicitly, this one is written explicitly. And whenever you have a function that's written implicitly, you find the derivative using implicit differentiation, which means that you're basically going to use the chain rule. Okay, so here's another example. I wrote one up above, but here is another equation that's written explicitly. And if you try to factor out a y on the left-hand side, notice the y squared messes that up. Okay, so I'm just showing you an example of what one will look like where you need to use implicit differentiation. And we're actually going to find the derivative of this one in just a minute. Okay, so these are the things that you have to remember when we start using implicit differentiation. Whenever we find dy dx, and you are differentiating a term that only has an x. So for instance, I'm just going to make one up here real quick. Okay, I only put one term in there. But we know that if you find the derivative with respect to x of 3x squared, you're just going to get 6x. That looks normal, right? So that's what I mean by you can differentiate as usual because there's no y in this term. When you differentiate a term involving y, you have to use the chain rule because in all of these problems, we are assuming that y is defined implicitly as a function of x, which means that it makes sense to find the derivative of y with respect to x. So that means that if I find the derivative with respect to x, excuse me just a second. Sorry about that. I had to cough for a second. If I find the derivative with respect to x of y to the fifth, I am going to use the chain rule because in this function, y is the inside function. Y is some function of x. So when I use the chain rule, I drop the 5 down, right? We decrease the exponent by 1. We evaluate that at the inside function. And then we multiply times the derivative of the inside function. Well, the derivative of y with respect to x is dy dx. So notice right here that I use the chain rule. So any questions about that before we go on? And if you can remember that every time you take the derivative of something with a y in it, that you have to use the chain rule, that really is where you're using implicit differentiation. Okay, and the derivative of the inside function, the derivative of y is dy dx. And once that you feel comfortable with that, you're going to do great with implicit differentiation. Okay, these guidelines that I have here for implicit differentiation. So keep those handy, and you can look at them as we do the next problem where we actually evaluate a derivative using implicit differentiation, because in every one of these problems, these are the steps. Okay, so this is the way I think about it when I'm finding the derivative. So notice that the first step is going to be to differentiate both sides of the equation with respect to x. Okay, so let's look at our problem. This is the one I had on an earlier slide. Okay, so when I see this problem on the quiz or the test, I notice that the x's and y's are all mixed together. That's how I know to use implicit differentiation. Y is not isolated. And so that means that I am going to take the derivative of both sides. And we know that if I take the derivative of the left-hand side, that's a sum, so I would take the derivative of each term. After we do a couple, I won't write that step down, but I want to make sure that you see that's what we're doing. So I'm just taking the derivative of each term with respect to x. And again, in all of these problems, y is some function of x. Okay? We just don't know what that is. So when I take the derivative of x squared y, notice that's a product. So that means you have to use the product rule. So that's what we're going to do right here. We're going to take that derivative using the product rule. And the product rule says you take the first one, which is x squared, times the derivative of the second, but the derivative of y with respect to x is dy dx. That's what we mean by dy dx. Plus the second one, which is y, times the derivative of the first. What's the derivative of x squared with respect to x? Yeah, that's 2x. So all of this is the derivative of that first term. So any questions about that before we go to the second term? If you didn't quite catch it, you probably will when we do the next one. So now we're going to take the derivative of y squared times x. It's very tempting to just take those derivatives and multiply them together, but remember that doesn't work. So make yourself think that's a product, so I have to use the product rule. And the product rule says I take that first function, y squared, times the derivative of the second, plus the second times the derivative of the first. So now I need to find the derivative of y squared. Whenever you take the derivative of something with a y in it, you have to use the chain rule. So we drop the 2 down, decrease the exponent by 1, but then we have to multiply times the derivative of the inside function. Sometimes it helps people to put a parenthesis around that y to kind of emphasize that the y is the inside function there. So all of this is the derivative of the second term. And what's the derivative on the right-hand side? What do I get? Yeah, the derivative of a constant is just 0. Very good. Okay, so that's the new step where we used implicit differentiation. Now we have to do a lot of algebra stuff because we need to isolate dy dx. But we know how to do that. It just looks kind of funny. But we are going to get all of the terms that have a dy dx on one side. So the x squared dy dx, I'm going to leave that on the left. I'm going to put the dy dx terms on the left-hand side. So notice this last one. I have a 2xy dy dx. And the terms that don't have a dy dx, I'm going to put on the right-hand side. So I'm going to subtract 2xy from both sides, and I'm going to subtract the y squared from both sides. So now we're just doing the algebra steps to isolate the dy dx. And once you get all of the dy dx terms on one side, then you can factor out the dy dx. These algebra steps look basically the same every time. If I factor out that dy dx, in this first term, I would have an x squared left. In the second term, I would have a 2xy. And we almost have it. So what do I need to do now to isolate dy dx? If I want dy dx by itself, good, I just need to divide both sides. That's exactly right. So we're going to divide by that parenthesis. So we'll have minus 2xy minus y squared divided by x squared plus 2xy. And that's it. When you use implicit differentiation, you will usually have both x's and y's on the right-hand side. So don't worry about that. But that is our derivative. The second dy dx in the orange came from, so let me highlight where that came from. So I think that you're asking about this one. Are you talking about this one? Yeah, so that was from the step before. So and is your question where it came from in this step that I had written in purple? Or I think that you meant when I copied it down to the line written in orange. But let me know if I didn't answer your question. Okay, so any other questions about that? Oh, where the purple dy dx came from? The purple dy dx came from right here. So again, let me just write this little part. Notice I'm using the product rule in this step. So I'm underlining the whole step. So I had the first one times the derivative of the second. The derivative of x is 1. Then when we use the product rule, it says the second one, the x came from here, times the derivative of the first. So when I take the derivative of y squared, remember y is some function of x. So I'm using the chain rule. So when I use the chain rule, it says I drop that 2 down, decrease the exponent by 1, evaluate that at the inside, but then I have to multiply times the derivative of the inside function. And the derivative of y with respect to x is dy dx. So that dy dx in purple came from taking the derivative of the inside function when we use the chain rule. Did I answer your question there, Daniel? Yes, the derivative of y is dy dx. That's exactly what we mean when we write dy dx. That means the derivative of y with respect to x. Yes. That looks like a G, but that's supposed to be a Y, the derivative of Y with respect to X. Great questions. All right, so let's try another one. It takes a while to get used to implicit differentiation, to kind of really catch what's going on. Okay, so in number 2, notice the X's and Y's are mixed together. Actually, Y is inside that cosine function. So, and after the next section or two, I think it's in 3.9, maybe 3.10, okay, and a couple of sections anyway, a couple of days. And one option might be to isolate y using an inverse trig function, and then you could take the derivative from there. But most of you probably wouldn't want to do that anyway. It's easier just to use implicit differentiation. So as soon as I see the x's and y's mixed together, I'm going to take the derivative of both sides with respect to x. All right, so that's our basic strategy, is we're taking the derivative of both sides with respect to x. And on the left-hand side, notice that we have a product. So we have to use the product rule. So 2 sine x is our first function, cosine y is the second function. So the product rule says that you take the first one times the derivative of the second plus the second one times the derivative of the first and the right-hand side, of course, is easier because the derivative of a constant is 0, so I just get a 0 over there. All right, but now we're going to take the derivative of cosine y. So that means that we're going to have to use the chain rule. Y is the inside function. So we take the derivative of the outside function, and the derivative of cosine x would be what? We take the derivative of cosine, what do we get? Good, minus sine. So we'll say minus sine, but we evaluate at that at the inside function, which was y. But then we have to multiply times the derivative of the inside function. And the derivative of y with respect to x is dy dx. So again, I used the chain rule there. Whoops, didn't mean to do that. Okay, then plus cosine y. The derivative of 2 sine x would be 2 cosine x. Okay, so any questions about that step? So just like in the last problem, once you do that, that's the new part. We've taken the derivative of all of those terms. Be really careful when you get to a term that has a y in it. And then we are going to get all of the terms with the dy dx on one side, the terms without a dy dx on the other side. So this time I have minus 2 sine x sine y times dy dx equals minus 2 cosine y cosine x. And I can divide on both sides to isolate dy dx. Notice when we divide, I'll have a minus 2 on top and a minus 2 on bottom. So those would cancel out. So we would end up with cosine y cosine x over sine x sine y. Okay, so I want you to have time to write that one down and think about it. I'm going to call roll real quick, but please let me know if you have a question about that one. But unmute and let me know that you're here when you hear me call your name. Jacob. Grace,
Here.
Jamie,
Here.
Casey, Garrett,
Here.
Christian, Michael,
Here.
Bryce.
Here.
Did anyone not hear me call your name? That's in that class that meets at this time regularly. Okay, so any questions about number 2 then before we go on to the one where we have to write the equation of the tangent line? Okay, the good news is you already know how to write equations of tangent lines, right? So the only part that's different is that you have to use implicit differentiation to find dy dx. And again, I know I need to use implicit differentiation because y is not isolated. Right? So as soon as you see that, just start taking the derivative at each term. Notice we already have our point. So we're given both the x and the y coordinate. This time they both happen to be 1, but of course it depends on what your function is. But notice if you plugged in 1 for x and 1 for y, that it would make our equation true to the left. So that really is a point on our curve. So we need the slope of the tangent line at that point. So we are going to find the derivative. Okay, so when we take the derivative of x to the third, there's no y in that term, so it looks normal, right? We know the derivative of x to the third with respect to x is 3x squared. Plus, we have to take the derivative of y to the third. Can you guys tell me what the derivative of y to the third is with respect to x? So if you know what it is, type it in for me. If you're not sure how to get it, let me know that too. That's a perfectly acceptable answer. Thank you for letting me know. Okay, that's how I know that we need to talk about these some more. Okay, so remember, every time that you take the derivative of a function with a y in it, think of it like this. If it helps you, put parentheses around the y. So the y is the inside function, right? And raising it to the third power is the outside function. So it's just like your homework for today. When we take that derivative, we start by taking the derivative of the outside function. So we drop that down, decrease the exponent by 1. And then we have to evaluate that at the inside function. So our inside function is y. And then we multiply that times the derivative of the inside function. And the derivative of y is dy dx. So we took the derivative of the outside function, evaluated at the inside, times the derivative of the inside. It takes a while to get the hang of that. So I really am glad that you let me know that that's still a little shaky. So we'll, keep coming back to it. But did that help? If we need to do another one where we just have a power without other stuff going on, we'll do that. Okay, so let's keep going, but you let me know if you're still having trouble with those in a little bit as we do more. Okay. On the right-hand side, what rule should I use? Oh, absolutely, Michael. Go ahead, what's your question? Feel free to unmute yourself if you just want to talk to me, or you can type it in, whichever you prefer. So just to make sure that I'm answering your question, when we take the derivative of x to the third, the derivative with respect to x of x to the third is 3x squared. Yes, I think that's what you're saying.
Right, but like since what you just said about using the chain rule for the y to the third,
Hmm.
we would technically like do that with x to the third, right? But since
You
one is
could,
just like anything times one is just the thing, then it's
right.
that part's ignored, right? Okay.
Right. I mean, you can't go wrong by thinking about it like that, but then when you multiply the derivative of the inside, just like you said, the derivative of the inside is one. So we usually don't say it like that.
Right, right.
Yeah.
I was just
Yeah.
trying to like understand that in relation to what we're also
Yeah.
learning with implicit as well.
Yeah. You absolutely could think of it like that. So that tells me that you are starting to think about the implicit differentiation correctly. So that's great. Okay. On the right-hand side, what rule do I need to use? Yes, Daniel, that's exactly right. You'll use the chain rule for every term that has a y in it. Yes. The product rule, very good. Okay, so we have the first one, which is 2x times the derivative of the second one. When I say the derivative, we mean the derivative with respect to x because we are finding dy dx. So the derivative of y with respect to x is dy dx plus the second one, which is y, times the derivative of the first, but the derivative of 2x is just 2. Okay, so notice that you don't get the dy dx every time you write a y. You get the dy dx every time that you take the derivative of something with a y in it, okay? Because that's the derivative of the inside function. And I'm going to start rearranging that, but I don't mind if you still ask a question about it. I'm going to start putting the dy dx terms on the left-hand side. And the terms without a dy dx, I'm writing on the right-hand side. And then we're going to factor out the dy dx. And every time after you do that, you'll be able to divide to isolate the dy dx. Yes, was someone going to ask a question?
Oh, my bad. I forgot to mute my mic.
Oh, no, that's okay. I like hearing from you. All right, so we're not finished yet. We've just found the derivative, right? So I drew a box around that like I was finished. So, but I'm not quite finished. But any questions about the derivative before we do anything else? All right, so now we have to finish the problem by writing the equation of the tangent line. So I'm going to use a new notation that I don't think that I've used in our class before. But when we have the derivative and we're going to evaluate it at that point, you'll often see it written like this. That means evaluate the derivative dy dx at the point 1, 1. So that means everywhere I have an x, I'm going to plug in 1. Everywhere I have a y, I plug in 1. You could have just written that as 2 minus 3. I just wanted to make sure that you could see where I've got the numbers. So I'm using this point that was given to me over here. So it looks like on top, I get -1. On bottom, I get +1. So the slope of our tangent line is -1. So the equation, everything, got lots of ones there. So I'm using my point. Y minus the y coordinate is equal to the slope times x minus the x coordinate. So any questions about the equation of our tangent line? So it's kind of like the other things we have done. The new part really is the implicit differentiation, taking derivatives of those terms that have a y in it. And then you're going to be answering the same types of questions as in the other sections. Okay, then now that we know how to find a first derivative, we're going to find a second derivative. And you already know that to find the second derivative, you take the derivative of the first derivative. But that can look a little funny when you use implicit differentiation. So, and you can refer back to those steps as you need to. I will say them as we're working this problem. But if you want to go back and, if you have them laying by you on a sheet of paper, you can refer to them. All right, but here is our problem. Notice it says find the second derivative of y with respect to x. Well, we know that the first thing we need to do is find the first derivative. So let's do that. Okay, so just like before, the x's and y's are mixed together. Notice if I subtract x from both sides, I still have an isolated y because I have this y that's in the argument of that trig function. So I'm going to use implicit differentiation. So I take the derivative of the first term. The derivative of x with respect to x is just 1. Plus, take the derivative of y with respect to x. Well, that's just dy dx. Equals. On the right-hand side, notice that y is inside that function. I think it really helps when you're first learning implicit differentiation if you'll put parentheses around it. Okay, so it's the inside function. I take the derivative of the outside function, evaluate it at the inside, and then I multiply that times the derivative of the inside function. The derivative of y with respect to x is dy dx. So any questions about that? So we're going through those same steps again. We want to get all the dy dx terms on one side. I'm going to put them on the left just because I usually do that for no really good reason. Okay, so I am going to subtract this. So I just subtracted that from both sides. I'm going to subtract 1 from both sides. So maybe it would have made more sense for me just to subtract that dy dx, right? But now I'm going to factor out the dy dx. So when I do that, I'm going to have 1 minus cosine y. And I get dy dx is minus 1 over 1 minus cosine y. I'm going to draw a box around that, but I'm not finished. Of course, that is just the first derivative, dy dx. But any questions about that first derivative before I go on? Okay, because now we're going to find the second derivative. Okay. But we know to find the second derivative, we take the derivative of the first derivative. So notice if I take the derivative of the left-hand side, and I'm going to take the derivative of the right-hand side. So on the left-hand side, the derivative of dy dx is the second derivative. When I write it like this, I hope you see where this notation comes from. It kind of looks like d squared, but remember, don't read that as d squared. We're really not squaring anything. That means the second derivative. On the right-hand side, when I take that derivative, what rule should I use? Yeah, we'll just use the quotient rule. So when we use the quotient rule, on the bottom, I have the bottom squared. On top, I have the bottom, which is 1 minus cosine y, times the derivative of the top, but the derivative of the top is just 0. Minus the top, so notice I would have minus minus 1, times the derivative of the bottom. So now I'm going to take the derivative of this denominator. The derivative of 1 is 0, minus the derivative of cosine y. Can you help me out there? What would be the derivative of minus cosine y? Good, we would get a sine y, good. But then we have to multiply times what? Dy dx, good. That's the derivative of the inside function. So remember that this is cosine of y. The y there is the inside function. And let's rewrite that to make it look better. So now I have sine y times dy dx over 1 minus cosine y squared. And I'm not quite finished, but any questions to there before I go on? Okay, the reason that I'm not finished there is because when we find the second derivative of y with respect to x, we want our answer to be a function of x and y, not a function of x and y and dy dx. Every time you find a second derivative, you're going to have a dy dx over here in your problem. And every time you're going to have to substitute that dy dx from your first derivative. We know what dy dx is equal to, so I'm going to plug it in there. So now I'm going to rewrite that. So I have sine y, but I'm going to substitute, instead of dy dx, I'm going to write minus 1 over 1 minus cosine y. And you'll have to do that every time. So if you, I'm going to scroll up, but I promise I'll bring it back. This is what I mean by this step. If you're looking at those steps, every time you find the second derivative, you're going to have to substitute by plugging that in. And I have to rewrite that. Never leave complex fractions in your answer. So I'm going to multiply the top and the bottom times 1 minus cosine y. So when I do that, on top, I'm going to have minus sine y. On bottom, I will have 1 minus cosine y to the third. And now I only have x's and y's for variables on the right-hand side. I don't have any complex fractions, so it's okay to leave it like that. I am going to talk about that last step that you see on the previous slide, but it's fine if you leave this one with the answer that I have in the box. So any questions about what we did there? The second derivative ones can be kind of long. I tried to pick out the ones that I assigned in my math lab that won't just kill you with the arithmetic because they can get quite messy. So be careful, just take your time. I want to talk about this last comment. If possible, substitute into the original equation to simplify your answer. I want to show you what I mean by that. This is a great example to show you. It depends on what you're doing with that, whether you would want to keep simplifying or not. So if you got to here, that's great. But sometimes you can make it better by going back to your original equation. Do you see that sine y is equal to x plus y? So you could, if for some reason you wanted to, replace this sine y in the numerator with x plus y because the original problem tells us that those are equal. You know, and usually when I would want to do that is if I had to find another derivative. I am really looking for things to make that answer look as nice as possible before I have to take the derivative again. So that's usually when I would really go back and look to see if there's another way that I could rewrite it. Sorry, this is kind of scrunched up here. I'm going to move this. Okay, but any questions about that? I didn't mean to move my little y there. Okay. So let's stop here and take a break so you can look at that during break and let that soak in. And that way you can figure out if you have a question about it to ask me. So take about 5 minutes and then we'll come back and finish those last examples. Hello, I'm back. So I'd appreciate if you'd let me know if you can hear me. I'll know you're back. Thanks, Jamie. Thanks, Grace. So as we're waiting for everyone to kind of get back to their computer, does anyone have a question about this example before we go on? Okay, then let's keep going. So for the next one, we are supposed to determine the points where the curve has a vertical tangent line, and then we are going to determine the points where we have a horizontal tangent line. So we can see the equation of our curve at the top. And if we are going to find out where we have a vertical and horizontal tangent line, then we need to know some information about those. And I know that we've seen this one in class before. If we have a horizontal tangent line, what do we know about the slope of that line? If a line is horizontal, what do we know about its slope? Yeah, it's 0. Good. And since we're talking about the tangent line, we know the derivative gives us the slope of the tangent line. So that means that dy dx would be 0 at those points where we have a horizontal tangent line. What do we know about the slopes of vertical lines? If a line is vertical, what do we know about its slope? Yeah, it's undefined. Very good. The slope is undefined. So that means that we are going to be looking for the places where dy dx is undefined, because that's where we will have a vertical tangent line. Okay, so to do either one of those, we need to find dy dx. So we're going to start there. On this particular one, it's definitely possible to algebraically solve for y, so you can do that if you want. I'm going to go ahead and use implicit differentiation. Well, and actually, it looks like I just have y minus y there, so those would actually just cancel out. I did not mean to do that, so I'm going to change that to an x times y. Sorry about that. Otherwise, it doesn't really make sense, okay? Well, it would make sense, but it would be, we wouldn't have to actually do any work. All right, so here is our curve, xy minus y equals 1. And we're going to find dy dx. So I'm going to use the product rule on the left-hand side. So I say the first times the derivative of the second plus the second times the derivative of the first. So all of that is the derivative of the first term. Minus y, I need to take the derivative of that. And the derivative of the right-hand side is 0. So I'm going to put all of the terms that have a dy dx on the left-hand side. And that term without a dy dx, I'm moving to the right. Now isolate dy dx, so I'm going to factor the dy dx out. And I've done that a couple of times now. So I'm kind of doing that a lot faster and just writing it down, but please stop me if I do a step that doesn't make sense. And so I get dy dx is equal to minus y over x minus 1. Okay, so that's my derivative. And we're going to go from there. So any questions about the dy dx part? Okay, so now we go back to the question. So the first question says that we want to know the points on the curve where the slope is undefined. And we got this fraction when we took the derivative, and we know that a fraction is undefined when the bottom is 0, right? So that means that this dy dx will be undefined when the denominator is equal to 0, or when x is equal to 1. So any questions about that part? Make sure you read the problem carefully. Notice it says determine the points on the curve. So that means we need both an x coordinate and a y coordinate. So we know that x is 1. To find y, we have to plug that back in to our original equation, just like we've done before. So I am plugging a 1 in for x. Okay, and if I do that in this problem, okay, so I'm going to notice I'm going to substitute in 1 for x. Do you see what happens? Do you see I get 0 equals 1? Yeah, that doesn't make any sense, right? 0 is not equal to 1. So that means this point where x equals 1 is not actually a point on the curve. The original function is undefined there as well. So that means that there are no places, no points on the curve where we have a vertical tangent line. That looks, I didn't mean to make that look funny there. Those are two different words, okay? So that turned out a little weird at the end. So any questions about that? The only place where we could possibly have a vertical tangent line turned out to not be a place where our original function was defined. Okay, but that's how you would find it. So lots of times when you do that, of course, you're going to get some value for y, so you would have an ordered pair. So let's see what happens when we find the next one. We're supposed to find out where we have a horizontal tangent line. Well, to find that place, you will always take your derivative and set it equal to 0. So notice if I take this derivative and set it equal to 0, I can multiply both sides times x minus 1. So in other words, usually we'll say that as a shortcut. We just set the top equal to 0 because we can always multiply times the denominator. So we would have a horizontal tangent line at the points where y equals 0. So any questions about that part? In this particular problem, we're going to have the same problem because remember, to find the point, we need to find the x coordinate that goes with it. If we go back to our original function and plug in 0 for y, notice once again, we would get 0 equals 1. That means that there is no point on our curve for y equals 0. So there are no points on our curve where we have a horizontal tangent line. But if we got some value for x there, then we would write the point, the x coordinate and the y coordinate. So any questions at all about that problem before we go on? Okay, so I have some more. Let's just make sure that you have the hang of implicit differentiation before you take your quiz. So again, we're going to do these in class, hoping that you get the hang of it, but make sure that you work these homework problems before you take the quiz as well. And we will get finished in time today, I hope, to give you some class time to work on the homework problems since the quiz is due tomorrow. You won't have time in class time to take the quiz, so I hope you have time to at least get started on your homework. Okay, so number 1, we are going to find dy dx. Notice the x's and y's are all mixed together. So I know I'm going to use implicit differentiation. So I'm going to take the derivative of each term. When I take the derivative of the left-hand side, I can see I need to drop down the 3, decrease the exponent by 1, evaluate that at the inside, times the derivative of the inside function. And you could go ahead and take that derivative of the inside function right there if you want. But on the right-hand side, I have the derivative with respect to x of x minus the derivative with respect to x of y squared. Can you tell me what I get when I take the derivative of y squared with respect to x? What's the derivative of y squared with respect to x? Very good, Michael. 2y to the first times the derivative of the inside. And the derivative of 8 is 0. So now I need to take the derivative of xy plus 1. So I'm going to use the product rule there. So we have 3 times xy plus 1 squared times the first times the derivative of the second plus the second times the derivative of the first, but the derivative of x is 1. The derivative of 1 is 0. So in that step, the calculus part is over. Okay, we have taken the derivative, but now we have to do some algebra stuff. So any questions to there? Dy dx is inside the parentheses on the left-hand side, so I am going to distribute this. So I will have 3x xy plus 1 squared dy dx plus 3y and every time we're going to have to put the dy dx terms on one side, so I'm going to put them on the left. And then what's the next step? Exactly, Jamie. Once you get all of the dy dx's on one side, the next step is to factor out the dy dx. And then you will be able to divide on both sides to isolate dy dx. You got lost in the green part. Okay, let's go back and look at that, Garrett. Okay. So in the green part is where I distributed. So notice I have this 3 times xy plus 1 squared here. So I multiplied that times the first term. That's where I got this. And then I multiplied that times the second term. That's where I got this. So I distributed through the parentheses. Yeah, we had to distribute everything that was in front of those parentheses. We had to distribute through the parentheses. Yeah, so notice there's, I think that you see now, but just to make sure, this was the part that was in front that I highlighted in orange. So I multiplied it times both of those terms in the parentheses. Thank you for stopping to ask about that. So this doesn't get too scrunched up. I'm just going to move this one down. Okay, but any other questions about this one before we go to the next one on your paper? No, I'm sorry, Michael. I feel your pain. I had that trouble yesterday. I don't know why it kept doing that, but it happens sometimes. Okay, so it sounds to me like you guys kind of figured out where the problem was on that one. So let's go to that next one that you see. You see the X's and Y's are mixed together. So we know we're going to use implicit differentiation. So I'm just going to take the derivative of each side. Okay, so on the left-hand side, I have e to some power. Okay, so we know when we take the derivative of e to some power, it's always itself times the derivative of the exponent. So we're using the chain rule there. All right, so that's what you did for today. So we'll do that, actually evaluate that derivative in another step. On the right-hand side, we have the derivative with respect to x of 2y. Can you tell me what the derivative of 2y is with respect to x? Very good. It's 2 times dy dx. Good. So on the left-hand side, we have to find the derivative of x times y. So just as a reminder, they're multiplied, so we have to use the product rule. So we have e to the xy times the first times the derivative of the second plus the second times the derivative of the first. And the dy dx on the left-hand side is inside those parentheses. So just like the last problem, we need to distribute to get rid of those parentheses. So I'm going to multiply the e to the xy through the parentheses. So I have to multiply every term times e to the xy. And then it starts looking easier because it looks like our other problems. I have all those terms separated now. I'm going to put all the dy dx terms on the same side. So I'm going to put them on the right-hand side this time so I don't have to move as much stuff around. get the dy dx's all on the same side, and then factor out the dy dx. And then we divide. So don't let it bother you if you see that exponential function in there. That's the same rules, and you know how to take the derivative of e to the something. It's always just itself times the derivative of the exponent. I didn't pause very much in that one since we've done several now, but I want to make sure that you have time to get it written down and ask questions. So let me know whether you have a question or if you got it and you're ready to go on, let me know that too. Thanks, Michael. What about everyone else? Of course, when you're working those homework problems today, feel free to email me questions if you think of something later. But let's go ahead and do one more, and then I'll let you go and get started on those. So the next one, we're trying to find the equation of the line that's normal to the curve. And we did a problem like that one other day in class. When we're finding the equation of a normal line, can anyone remind me, what does it mean when we have a normal line? Does anybody remember from the other problem we did in class? So I'm just kind of sketching a curve over here for while I'm waiting to see if anybody remembers. So we know here is the tangent line, but this time we are finding the equation of the normal line. Good. The normal line is perpendicular to the tangent line at that point. So when we are asked to find the equation of the normal line, we're basically going to have to use the same strategy to work it. We need to find dy dx to find the slope of the tangent line. And then we know the slope of the normal line will be the negative reciprocal of the slope of the tangent line. So the real work is finding the derivative, dy dx. Okay, so here is our equation. And I want you to help me more this time. What is the derivative of sine y with respect to x? When we take the derivative of the first term, what will I get? Good, we'll get a cosine, good. So I'll get cosine of what? But you're exactly right. I'm definitely going to get a cosine. Cosine of y, good. Cosine of y times dy dx. The derivative of 5x is 5. And you've told me this one a couple of times this morning. The derivative of y squared with respect to x is 2y dy dx. So it looks to me like you're getting the hang of it. So again, I'm going to subtract to get the dy dx's on the same side. And then I'm going to factor out the dy dx. Okay, so we're not finished, but we have the derivative. So any questions about finding that derivative before we go on? Okay, and once that we have the derivative, how do we find the slope of the tangent line? What do we do to find the slope of the tangent line? Yeah, we have to plug in, only this time we have an X and a Y, but you're exactly right. We have to plug in our point. So we are going to take our derivative and we have to plug in our point. So everywhere there's an X, we're going to put in pi squared over 5. Everywhere there is a Y, we're going to put pi. So it looks like we'll have 5 over 2 pi minus cosine of pi. But what is cosine of pi? Yeah, -1. Very good. So we end up with 5 over 2 pi plus 1. So that's the slope of the tangent line, but we want the slope of the normal line. So the slope of the normal line would be what? What do we have to do to that to get the slope of the normal line? Good. We have to take the opposite reciprocal. Very good. So I'm going to have minus 2 pi plus 1 over 5. So you could put the minus out front if you want. I'm just going to put it there. Okay, whichever. Same thing, right? I just wanted to make sure that it didn't just look like it was in front of the 2 pi. So we take the negative reciprocal. And once we have the slope of the normal line, we can write the equation of the normal line. So we would say y minus the y coordinate is equal to the slope times x minus the x coordinate. And we could distribute that and add pi, but usually if it looks kind of messy like that, I would just tell you to leave it in point slope form. That's really the advantage to using point slope form instead of using y equals mx plus b and plugging in numbers and solving for b. That's fine, but if you do that, you have to deal with that messy arithmetic.